Section 11 of the Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit librivox.org. Recording by J. C. Guan. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 11. Part 7. The Dawn of Mind. In the story of evolution, there is no chapter more interesting than the emergence of mind in the animal kingdom. But it is a difficult chapter to read, partly because mind cannot be seen or measured, only inferred from the outward behavior of the creature, and partly because it is almost impossible to avoid reading ourselves into the much simpler animals. Part 1. Two extremes to be avoided. The one extreme is that of uncritical generosity, which credits every animal, like Brer Rabbit, who by the way was the hare, with human qualities. The other extreme is that of thinking of the animal as if it were an automatic machine, in the working of which there is no place or use for mind. Both these extremes are to be avoided. When Professor Weismann took the eggs of the passenger pigeon, which became extinct not long ago with startling rapidity, and placed them a few inches to one side of the nest, the bird looked a little uneasy and put her beak under her body as if to feel for something that was not there. But she did not try to retrieve her eggs, close at hand as they were. In a short time she flew away altogether. This shows that the mind of the pigeon is in some respects very different from the mind of man. On the other hand, when a certain clever dog, carrying a basket of eggs, with the handle in his mouth, came to a stile which had to be negotiated, he laid the basket on the ground, pushed it gently through a low gap to the other side, and then took a running leap over. We dare not talk of this dog as an automatic machine. A caution in regard to instinct. In studying the behavior of animals, which is the only way of getting at their mind, for it is only of our own mind that we have direct knowledge, it is essential to give prominence to the fact that there has been throughout the evolution of living creatures a strong tendency to enregister or engrain capacities of doing things effectively. Thus, certain abilities come to be inborn. They are parts of the inheritance, which will express themselves whenever the appropriate trigger is pulled. The newly born child does not require to learn its breathing movements, as it afterwards requires to learn its walking movements. The ability to go through the breathing movements is inborn, ingrained, and registered. In other words, there are hereditary prearrangements of nerve cells and muscle cells which come into activity almost as easily as the beating of the heart. In a minute or two the newborn pigling creeps close to its mother and sucks milk. It has not to learn how to do this, any more than we have to learn to cough or sneeze. Thus animals have many useful ready-made, or almost ready-made, capacities of doing apparently clever things. In simple cases of these inborn prearrangements we speak of reflex actions; in more complicated cases, of instinctive behavior. Now the caution is this, that while these inborn capacities usually work well in natural conditions, they sometimes work badly when the ordinary routine is disturbed. We see this when a pigeon continues sitting for many days on an empty nest, or when it fails to retrieve its eggs only 2 inches away. But it would be a mistake to call the pigeon, because of this, an unutterably stupid bird. We have only to think of the achievements of homing pigeons to know that this cannot be true. we must not judge animals in regard to those kinds of behavior which have been handed over to instinct, and go badly agree when the normal routine is disturbed. In 99 cases out of 100, the unregistered instinctive capacities work well, and the advantage of their becoming stereotyped was to leave the animal more free for adventures at a higher level. Being a slave of instinct may give the animal a security that enables it to discover some new home, or new food, or new joy. Somewhat in the same way, a man of methodical habits, which he has himself established, may gain leisure to make some new departure of racial profit. When we draw back our finger from something very hot, or shut our eye to avoid a blow from a rebounding branch, we do not will the action; and this is more or less the case, probably, when a young animal sucks its mother for the first time. Some mound birds of Celebes lay their eggs in warm volcanic ash by the shore of the sea, others in a great mass of fermenting vegetation. It is inborn in the newly hatched bird to struggle out as quickly as it can from such a strange nest, else it will suffocate. If it stops struggling too soon, it perishes, for it seems that the trigger of the instinct cannot be pulled twice. Similarly, when the eggs of the turtle, that have been laid in the sand of the shore, hatch out, the young ones make instinctively for the sea. Some of the crocodiles bury their eggs 2 feet or so below the surface, among sand and decaying vegetation, an awkward situation for a birthplace. When the young crocodile is ready to break out of the eggshell, just as a chick does at the end of the 3 weeks of brooding, it utters instinctively a piping cry. On hearing this, the watchful mother digs away the heavy blankets, otherwise the young crocodile would be buried alive at birth. Now there is no warrant for believing that the young mound birds, young crocodiles, and young turtles have an intelligent appreciation of what they do when they are hatched. They act instinctively, as to the manner born. But this is not to say that their activity is not backed by endeavor, or even suffused with a certain amount of awareness. Of course, it is necessarily difficult for man, which is so much a creature of intelligence, to get even an inkling of the mental side of instinctive behavior. In many of the higher reaches of animal instinct, as in courtship or nest building, in hunting or preparing the food, it looks as if the starting of the routine activity also rang up the higher centers of the brain, and put the intelligence on the qui-vive, ready to interpose when needed. So the twofold caution is this: 1. We must not depreciate the creature too much, if, in unusual circumstances, it acts in an ineffective way along lines of behavior which are normally handed over to instinct; and 2. We must leave open the possibility that even routine instinctive behavior may be suffused with awareness and backed by endeavor. Part II. A useful law. But how are we to know when to credit the animal with intelligence, and when with something less spontaneous? Above all, how are we to know when the effective action, like opening the mouth the very instant it is touched by food, in the mother's beak, is just a physiological action like coughing or sneezing, and when there is behind it a mind at work? The answer to this question is no doubt that given by Professor Lloyd Morgan, who may be called the founder of comparative psychology, that we must describe the piece of behavior very carefully, just as it occurred, without reading anything into it, and that we must not ascribe it to a higher faculty if it can be satisfactorily accounted for in terms of a lower one. In following this principle, we may be sometimes niggardly, for the behavior may have a mental subtlety that we have missed, but in 9 cases out of 10 our conclusions are likely to be sound. It is the critical, scientific way. Bearing this law in mind, let us take a survey of the emergence of minds among backboned animals. Senses of fishes. Fishes cannot shut their eyes, having no true lids, but the eyes themselves are very well developed, and the vision is acute, especially for moving objects. Except in grizzly fishes, the external opening to the ear has been lost, so that sound waves and coarser vibrations must influence the inner ear, which is well developed, through the surrounding flesh and bones. It seems that the main use of the ear in fishes is in connection with balancing, not with hearing. In many cases, however, the sense of hearing has been demonstrated. Thus fishes will come to the side of a pond to be fed when a bell is rung, or when a whistle is blown by someone not visible from the water. The fact that many fishes pay no attention at all to loud noises does not prove that they are deaf, for an animal may hear a sound and yet remain quite indifferent or irresponsive. This merely means that the sound has no vital interest for the animal. Some fishes, such as bullhead and dogfish, have a true sense of smell, detecting by their nostrils very dilute substances permeating the water from a distance. Others, such as members of the cod family, perceive their food in part at least by the sense of taste, which is susceptible to substances near at hand and present in considerable quantity. This sense of taste may be located on the fins as well as about the mouth. At this low level the senses of smell and taste do not seem to be very readily separated. The chief use of the sensitive line or lateral line, seen on each side of a bony fish, is to make the animal aware of slow vibrations and changes of pressure in the water. The skin responds to pressures, the ear to vibrations of high frequency. The lateral line is between the two in its function. Interesting ways of fishes. The brain of the ordinary bony fish is at a very low level. Thus the cerebral hemispheres, destined to become more and more the seats of intelligence, are poorly developed. In grizzly fishes, like skates and sharks, the brain is much more promising. But although the state of the brain does not lead one to expect very much from a bony fish like trout or eel, haddock or herring, illustrations are not wanting of what might be called pretty pieces of behavior. Let us select a few cases. The stickleback's nest. The three-spined and two-spined sticklebacks live equally well in fresh or salt water. The larger 15-spined stickleback is entirely marine. In all three species the male fish makes a nest, in fresh or brackish water, in fresh or brackish water in the first two cases, in shore pools in the third case. The little species use the leaves and stems of water plants. The larger species use seaweed and zoophyte. The leaves or fronds are entangled together and fastened by glue-like threads, secreted, strange to say, by the kidneys. It is just as if a temporary disease condition had been regularized and turned to good purpose. Going through the nest several times, the male makes a little room in the middle. Partly by coercion and partly by coaxing, he induces a female, first one and then another, to pass through the nest with two doors, depositing eggs during her short sojourn. The females go on their way, and the male mounts guard over the nest. He drives off intruding fishes much bigger than himself. When the young are hatched, the male has for a time much to do, keeping his charges within bounds until they are able to move about with agility. It seems that sticklebacks are short-lived fishes, probably breeding only once, and it is reasonable to suppose that their success as a race depends to some extent on the paternal care. Now, if we could believe that the nesting behavior had appeared suddenly in its present form, we should be inclined to credit the fish with considerable mental ability. But we are less likely to be so generous if we reflect that the routine has been in all likelihood the outcome of a long gradual process of slight improvements and critical testings. The secretion of the glue probably came about as a pathological variation. Its utilization was perhaps discovered by accident. The types that had wit enough to take advantage of this were most successful. The routine became enregistered hereditarily. The stickleback is not so clever as it looks. The mind of a minnow. To find solid ground on which to base an appreciation of the behavior of fishes, it is necessary to experiment, and we may refer to Miss Gertrude White's interesting work on American minnows and sticklebacks. After the fishes had become quite at home in their artificial surroundings, their lessons began. Cloth packets, one of which contained meat and the other cotton, were suspended at opposite ends of the aquarium. The mud minnows did not show that they perceived either packet, though they swarmed close by them. The sticklebacks were intrigued at once. Those that went towards the packet containing meat darted furiously upon it, and pulled at it with great excitement. Those that went towards the cotton packet turned sharply away when they were within about 2 inches off. They then perceived what those at the other end were after, and joined them, a common habit amongst fishes. Although the minnows are not interested in the tiny bags of mystery, they were even more alert than the sticklebacks in perceiving moving objects, in or on the water, and there is no doubt that both these shallow water species discover their food largely by sense of sight. The next set of lessons had to do with color associations. The fishes were fed on minced snail, chopped earthworm, fragments of liver, and the like, and the food was given to them from the ends of forceps held above the surface of the water, so that the fishes could not be influenced by smell. They had to leap out of the water to take the food from the forceps. Discs of colored cardboard were slipped over the end of the forceps, so that what the fishes saw was a morsel of food in the center of a colored disc. After a week or so of preliminary training, they were so well accustomed to the colored discs that the presentation of one served as a signal for the fishes to dart to the surface and spring out of the water. When baits of paper were substituted for food, the fishes continued to jump at the discs. When, however, a blue disc was persistently used for the paper bait, and a red disc for the real food, or vice versa, some of the minnows learned to discriminate infallibly between shadow and substance, both when these were presented alternatively and when they were presented simultaneously. This is not far from the dawn of mind. In the course of a few lessons, both minnows and sticklebacks learned to associate particular colors with food, and other associations were also formed. A kind of lava that a minnow could make nothing of after repeated trials was subsequently ignored. The approach of the experimenter, or anyone else, soon began to serve as a food signal. There can be no doubt that in the ordinary life of fishes there is a process of forming useful associations and suppressing useless responses. Given an inborn repertory of profitable movements that require no training, given the power of forming associations such as those we have illustrated, and given a considerable degree of sensory alertness along certain lines, fishes do not require much more. And in truth they have not got it. Moving with great freedom in 3 dimensions in a medium that supports them and is very uniform and constant, able in most cases to get plenty of food without fatiguing exertions, and to dispense with it for considerable periods if it is scarce, multiplying usually in great abundance so that the huge infantile mortality hardly counts, rarely dying a natural death, but usually coming with their strength unabated to a violent end, fishes hold their own in the struggle for existence without much in the way of mental endowment. Their brain has more to do with motion than with mentality, and they have remained at a low psychical level. Yet, just as we should greatly misjudge our own race if we confined our attention to everyday routine, so in our total, as distinguished from our average, estimate of fishes, we must remember the salmon surmounting the falls, the worry trout eluding the angler's skill, the common mud skipet Periophthalmus of many tropical shores, which climbs on the rocks and the roots of the mangrove trees, or actively hunts small shore animals. We must remember the adventurous life history of the eel and the quaint ways in which some fishes, males especially, look after their family. The male seahorse puts the eggs in his breast pocket. The male curtus carries them on the top of his head. The cock-pedal, or lumpsucker, guards them and aerates them in a corner of a shore pool. III. The Mind of Amphibians. Towards the end of the age of the Old Red Sandstone, or Devonian, a great step in evolution was taken, the emergence of amphibians. The earliest representatives had fish-like characters even more marked than those which may be discerned in the tadpoles of our frogs and toads, and there is no doubt that amphibians sprang from a fish stock. But they made great strides, associated in part with their attempts to get out of the water on to dry land. From fossil forms we cannot say much in regard to soft parts, but if we consider the living representatives of the class, we may credit amphibians with such important acquisitions as fingers and toes, a three-chambered heart, true ventral lungs, a drum to the ear, a mobile tongue, and vocal cords. When animals began to be able to grasp an object, and when they began to be able to utter sufficient sounds, two new doors were opened. Apart from insects, whose instrumental music had probably begun before the end of the Devonian age, amphibians were the first animals to have a voice. The primary meaning of this voice was doubtless, as it is today in our frogs, a sex-call, but it was the beginning of what was destined to play a very important part in the evolution of the mind. In the course of ages, the significance of the voice broadened out. It became a parental call. It became an infant's cry. Broadening still, it became a very useful means of recognition amongst kindred, especially in the dark and in the intricacies of the forest. Ages passed, and the voice rose in another turn of the evolutionary spiral, to be expressive of particular emotions beyond the immediate circle of sex. Emotions of joy and of fear, of jealousy and of contentment. Finally we judge the animal, perhaps the bird was first, began to give utterance to particular words, indicative not merely of emotions, but of particular things with an emotional halo, such as food, enemy, home. Long afterwards words became, in man, the medium of reasoned discourse. Sentences were made and judgments expressed. But was not the beginning in the croaking of amphibia? Senses of amphibians. Frogs have good eyes, and the toad's eye are jewels. There is evidence of precise vision in the neat way in which a frog catches a fly, flickering out its tongue, which is fixed in front and loose behind. There is also experimental proof that a frog discriminates between red and blue, or between red and white. And an interesting point is that while our skin is sensitive to heat rays but not to light, the skin of the frog answers back to light rays as well. Professor Yerkes experimented with a frog which had to go through a simple labyrinth if it wished to reach a tank of water. At the first alternative between two paths, a red card was placed on the wrong side and a white one on the other. When the frog had learned to take the correct path, marked by the white card, Professor Yerkes changed the cards. The confusion of the frog showed how thoroughly it had learned its lesson. We know very little in regard to sense of smell or taste in amphibians, but the sense of hearing is well developed, more developed than might be inferred from the indifference that frogs show to almost all sounds except the croaking of their kindred and splashes in the water. The toad looks almost sagacious when it is climbing up a bank, and some of the tree frogs are very alert. But there is very little that we dare say about the amphibian mind. We have mentioned that frogs may learn the secret of a simple maze, and toads sometimes make for a particular spawning pond from a considerable distance. But an examination of their brains, occupying a relatively small part of the broad, flat skull, warns us not to expect much intelligence. On the other hand, when we take frogs along a line that is very vital to them, namely, the discrimination of palatable and unpalatable insects, we find by experiment that they are quick to learn and that they remember their lessons for many days. Frogs sometimes deposit their eggs in very unsuitable pools of water, but perhaps that is not quite so stupid as it looks. The egg-laying is a matter that has been, as it were, handed over to instinctive registration. Experiments in Parental Care. It must be put to the credit of amphibians that they have made many experiments in methods of parental care, as if they were feeling their way to new devices. A common frog lays her clumps of eggs in the cradle of the water, sometimes far over 1,000 together. The toad winds 2 long strings round and between water weeds, and in both cases that is all. There is no parental care, and the prolific multiplication covers the enormous infantile mortality. This is the spawning solution of the problem of securing the continuance of the race. But there is another solution, that of parental care, associated with an economical reduction of the number of eggs. Thus the male of the nurse frog, Alites, not uncommon on the continent, fixes a string of 20 to 50 eggs to the upper part of his hind legs, and retires to his hole, only coming out at night to get some food and to keep up the moisture about the eggs. In 3 weeks, when the tadpoles are ready to come out, he plunges into the pond and is freed from his living burden and his family cares. In the case of the thoroughly aquatic Surinam toad, Pipa, the male helps to press the eggs, perhaps 100 in number, onto the back of the female, where each sinks into a pocket of skin with a little lid. By and by fully formed young toads jump out of the pockets. In the South American tree frogs called Nototrema, there is a pouch on the back of the female, in which the eggs develop, and it is interesting to find that in some species what come out are ordinary tadpoles, while in other species the young emerge as miniatures of their parents. Strangest of all, perhaps, is the case of Darwin's frogs, Rhinoderma of Chile, where the young, about 10 to 15 in number, develop in the male's croaking sacs, which become in consequence enormously distended. Eventually the strange spectacle is seen of miniature frogs jumping out of their father's mouth. Needless to say, we are not citing these methods of parental care as examples of intelligence, but perhaps they correct the impression of amphibians as a rather humdrum race. Whatever be the mental aspect of the facts, there has certainly been some kind of experimenting, and the increase of parental care, so marked in many amphibians, with associated reduction of the number of offspring, is a finger-post on the path of progress. Part IV. The Reptilian Mind. We speak of the wisdom of the serpent, but it is not very easy to justify the phrase. Among all the multitude of reptiles, snakes, lizards, turtles, and crocodiles, a motley crowd, we cannot see much more than the occasional traces of intelligence. The inner life remains a tiny rill. No doubt many reptiles are very effective, but it is an instinctive rather than an intelligent efficiency. The well-known soft-shell tortoise of the United States swims with powerful strokes, and runs so quickly that it can hardly be overtaken. It hunts vigorously for crayfish and insect larvae in the rivers. It buries itself in the mud when cold weather comes. It may lie on a floating log ready to slip into the water at a moment's notice. It may bask on a sunny bank or in the warm shallows. Great wariness is shown in choosing times and places for egg-laying. The mother tramps the earth down upon the buried eggs. All is effective. Similar statements might be made in regard to scores of other reptiles, but what we see is almost wholly of the nature of instinctive routine, and we get little glimpse of more than efficiency and endeavor. In a few cases there is proof of reptiles finding their way back to their homes from a considerable distance, and recognition of persons is indubitable. Gilbert White remarks of his tortoise, whenever the good old lady came in sight, who had waited on it for more than 30 years, it always hobbled with awkward alacrity towards its benefactress, while to strangers it was altogether inattentive. Of definite learning there are a few records. Thus Professor Yerkes studied a sluggish turtle of retiring disposition, taking advantage of its strong desire to efface itself. On the path of the darkened nest of damp grass he interposed a simple maze in the form of a partition box. After wandering about constantly for 35 minutes, the turtle found its way through the maze by chance. 2 hours afterwards it reached the nest in 15 minutes, and after another interval of 2 hours it only required 5 minutes. After the third trial the routes became more direct, there was less aimless wandering. The time of the 20th trial was 45 seconds, that of the 30th 40 seconds. In the 30th case the path followed was quite direct, and so it was on the 50th trip, which only required 35 seconds. Of course the whole thing did not amount to very much, but there was a definite learning, a learning from experience, which has played an important part in the evolution of animal behavior. Comparing reptiles with amphibians, we may recognize an increased masterliness of behavior and a hint of greater plasticity. The records of observers who have made pets of reptiles suggest that the life of feeling or emotion is growing stronger, and so do stories, if they can be accepted, which suggest the beginning of conjugal affection. The error must be guarded against of interpreting in terms of intelligence what is merely the outcome of long-continued structure adaptation. When the limbless lizard called the slow worm is suddenly seized by the tail, it escapes by surrendering the appendage, which breaks across a preformed weak plane. But this is a reflex action, not a reflective one. It is comparable to our sudden withdrawal of our finger from a very hot cinder. The egg-eating African snake, Dasypeltis, gets the egg of a bird into its gullet unbroken, and cuts the shell against downward projecting sharp points of the vertebrae, none of the precious contents is lost, and the broken empties are returned. It is admirable, indeed unsurpassable, but it is not intelligent. Part 5. Mind in Birds. Sight and hearing are highly developed in birds, and the senses, besides pulling the triggers of inborn efficiencies, supply the raw materials for intelligence. There is some truth, though not the whole truth, in the old philosophical dictum, that there is nothing in the intellect which was not previously in the senses. Many people have admired the certainty and alacrity with which gulls pick up a fragment of biscuit from the white wake of a steamer, and the incident is characteristic. In their power of rapidity alerting the focus of the eye, birds are unsurpassed. To the sense of sight in birds, the sense of hearing comes a good second. A twig breaks under our feet, and out sounds the dagger call of the bird we were trying to catch. Many young birds, like partridges, respond when 2 or 3 hours old to the anxious warning note of the parents, and squat motionless on the ground, though other sounds, such as the excited clucking of a foster-mother hen, leave them indifferent. They do not know what they are doing when they squat. They are obeying the living hand of the past which is within them. Their behavior is instinctive. But the present point is the discriminating quality of the sense of hearing, and that is corroborated by the singing of birds. It is emotional art, expressing feeling in the medium of sound. On the part of the females who are supposed to listen, it betokens a cultivated ear. As to the other senses, touch is not highly developed, except about the bill, where it reaches a climax in birds like the woodcock, which probe for unseen earthworms in the soft soil. Taste seems to be poorly developed, for most birds bolt their food, but there is sometimes an emphatic rejection of unpalatable things, like toads and caterpillars. Of smell in birds little is known, but it has been proved to be present in certain cases, e.g., in some nocturnal birds of prey. It seems certain that it is by sight, not by smell, that the eagles gather to the carcass. But perhaps there is more smell in birds than they're usually credited with. One would like to experiment with the oil from the preen gland of birds, to see whether the scent of this does not help in the recognition of kin by kin at night, or amid the darkness of the forest. There may be other senses in birds, such as a sense of temperature and a sense of balance, but no success has attended the attempts made to demonstrate a magnetic sense, which has been impatiently postulated by students of bird migration, in order to explain how birds find their way. The big fact is that in birds there are 2 widely open gateways of knowledge, the sense of sight and the sense of hearing. Instinctive aptitudes. Many a young water bird, such as a coot, swims right away when it is tumbled into water for the first time. So chicks peck without any learning or teaching. Very young ducklings catch small moths that flit by, and young plovers lie low when the danger signal sounds. But birds seem strangely limited as regards many of these instinctive capacities. Limited when compared with the little-brained ants and bees, which have from the first such a rich repertory of ready-made cleverness. The limitation in birds is of great interest, for it means that intelligence is coming to its own, and is going to take up the reins at many corners of the daily round. Professor Lloyd Morgan observed that his chickens incubated in the laboratory had no instinctive awareness of the significance of their mother's cluck when she was brought outside the door. Although thirsty and willing to drink from a moistened finger-tip, they did not instinctively recognize water, even when they walked through a saucerful. Only when they happened to peck their toes as they stood in the water did they appreciate water as the stuff they wanted, and raise their bills up to the sky. Once or twice they actually stuffed their crops with worms of red worsted. Instinctive aptitudes, then, the young birds have, but these are more limited than in ants, bees, and wasps, and the reason is to be found in the fact that the brain is now evolving on the track of what Sir Ray Lankester has called educability. Young birds learn with prodigious rapidity. The emancipation of the mind from the tyranny of hereditary obligations has begun. Young birds make mistakes, like the red worsted mistake, but they do not make the same mistakes often. They are able to profit by experience in a very rapid way. We do not mean that creatures of the little brain type, like ants, bees, and wasps, are unable to profit by experience, or are without intelligence. There are no such hard and fast lines. We mean that in the ordinary life of insects the unregistered instinctive capacities are on the whole sufficient for the occasion, and that intelligent educability is very slightly developed. Nor do we mean that birds are quite emancipated from the tyranny of ingrained instinctive obligations, and can always ring up intelligence in a way that is impossible for the stereotyped bee. The sight of a pigeon brooding on an empty nest, while her eggs lie disregarded only a couple of inches away, is enough to show that along certain lines birds may find it impossible to get free from the trammels of instinct. The particular interest of birds is that they have many instincts, and yet a notable power of learning intelligently. Intelligence cooperating with instinct. Professor Lloyd Morgan was foster parent to two moorhens which grew up in isolation from their kindred. They swam instinctively, but they would not dive, neither in a large bath nor in a current. But it happened one day when one of these moorhens was swimming in a pool on a Yorkshire stream that a puppy came barking down the bank and made an awkward feint towards the young bird. In a moment the moorhen dived, disappeared from view, and soon partially reappeared, his head just peeping above the water beneath the overhanging bank. This was the first time the bird had dived, and the performance was absolutely true to type. There can be little doubt as to the meaning of this observation. The moorhen has an hereditary or instinctive capacity for swimming and diving, but the latter is not so easily called into activity as the former. The particular moorhen in question has enjoyed about 2 months of swimming experience, which probably counted for something, but in the course of that experience nothing had pulled the trigger of the diving capacity. On an eventful day the young moorhen saw and heard the dog. It was emotionally excited. It probably did, to some extent, intelligently appreciate a novel and meaningful situation. Intelligence cooperated with instinct, and the bird dived appropriately. Birds have inborn predispositions to certain effective ways of pecking, scratching, swimming, diving, flying, crouching, lying low, nest building, and so on, but they are marked off from the much more purely instinctive ants and bees by the extent to which individual nurture seems to mingle with the inherited nature. The two together result in the fine product which we called the bird's behavior. After Lloyd Morgan's chicks had tried a few conspicuous and unpalatable caterpillars, they had no use for any more. They learned in their early days with prodigious rapidity, illustrating the deep difference between the pig-brain type, relatively poor in its endowment of instinctive capacities, but eminently educable, and the little brain type, say, of ants and bees, richly endowed with instinctive capacities, but very far from being quick or glad to learn. We owe it to Sir Ray Lankester to have made it clear that these two types of brain are, as it were, on different tacks of evolution, and should not be directly pitted against one another. The little brain type makes for a climax in the ant, where instinctive behavior reaches a high degree of perfection. The big brain type reaches its climax in horse and dog, in elephant and monkey. The particular interest that attaches to the behavior of birds is in the combination of a good deal of instinct with a great deal of intelligent learning. This is well illustrated when birds make a nest out of new materials, or in some quite novel situation. It is clearly seen when birds turn to some new kind of food, like the key parrot, which attacks the sheep in New Zealand. Some young woodpeckers are quite clever in opening fir cones to get at the seeds, and this might be hastily referred to as well-defined hereditary capacity. But the facts are that the parents bring their young ones first to the seeds themselves, then partly open cones, and then intact ones. There is an educative process, and so it is in scores of cases. Using their wits. When the Greek eagle lifts the Greek tortoise in its talons, and lets it fall from a height so that the strong carapace is broken and the flesh exposed, it is making intelligent use of an expedient. Whether it discovered the expedient by experimenting, as is possible, or by chance, as is more likely, it uses it intelligently. In the same way, herring gulls lift sea urchins and clams in their bills, and let them fall on the rocks so that the shells are broken. In the same way, rooks deal with fresh-water mussels. The thrush anvil. A very instructive case is the behavior of the song thrush when it takes a wood snail in its beak and hammers it against a stone, its so-called anvil. To a young thrush, which she had brought up by hand, Miss Frances Pitt offered some wood snails, but it took no interest in them until one put out its head and began to move about. The bird then pecked at the snail's horns, but was evidently puzzled when the creature retreated within the shelter of the shell. This happened over and over again, the thrush's inquisitive interest increasing day by day. It pecked at the shell and even picked it up by the lip, but no real progress was made till the 6th day, when the thrush seized the snail and beat it on the ground as it would a big worm. On the same day it picked up a shell and knocked it repeatedly against the stone, trying first one snail and then another. After 15 minutes' hard work, the thrush managed to break one, and after that it was all easy. A certain predisposition to beat things on the ground was doubtless present, but the experiment showed that the use of an anvil could be arrived at by an untutored bird. After prolonged trying, it found out how to deal with a difficult situation. It may be said that in more natural conditions this might be picked up by imitation, but while this is quite possible, it is useful to notice that experiments with animals lead us to doubt whether imitation counts for nearly so much as used to be believed. End of Section 11.